morning, students. Welcome to some of the concluding lectures of the Simulations of Business Systems course. And we have been going through quite a lot of tools, techniques and topics that are very pertinent to the business world. And we have seen what's a simulation, different aspects of simulation, different considerations in simulations, some of the software that are available, expensive software and other options that are available in simulation. And we also saw some of the simple things like Monte Carlo simulations, how to use hand simulation to study simple systems, how to use Arena to study complicated systems, etc. And we also seen one of the very advanced software tools called as Technomatics, which is made by Siemens, which is very expensive, close to a couple crores of license rupees in license fees. And since it's a short course, we are now going to conclude into major aspects of it. And one of the things that we did not cover quite a lot in the class is about probability distributions. We were just using them exponential and other things without getting into much details of it. So we thought it is better to conclude the lecture by giving you a good idea about probability distributions, and hopefully in that process you will be able to understand the importance of it. But I still recommend you guys, this is not a probability in statistics course. So hence there is a limitation to how much of probability distributions can be covered. So whatever will be covered in this class will be pertaining to what is relevant in the simulation world. Okay, and I am assuming that somewhere or other you guys will somehow learn the basics of it, and let's see what all things I can cover and when do we use what simulation, what distribution in the simulation is what I will try to cover today. So if you look in the today's topic, what we are talking is probability distributions 1, and I'll try to bring a second small set of presentation, probability distributions 2, in which we will have some more details of the distribution. The major topics, the learning agenda today is we talk about random variables and simulations or random variates. Okay, why, what is the significance? With respect to simulation. This is what we will be discussing today. And then the question is, how do we choose? Second one, choosing the right distribution. How do you choose? Okay, the criteria. What are the criteria? That is what we actually will be doing in the second part of it. Then there is lot of books. Depending upon which book you refer, you will get different values. So in this case, what we are trying to do is how it is done in industry. The practitioner's role. What do the industry do? Okay, and what are the mistakes? Okay. So this is the main aspects that we will be covering here. Then we think about the PDF and CDF, which is probability density distribution function. So this is the probability distribution function. This is for discrete random variables, and also it is probability density function for continuous RV, continuous random variables. Okay. Similarly, CDF is this is, you can think about it as cumulative distribution function. It is for the discrete, or it can also be the cumulative density function for continuous. Okay. So we will see the fundamental thoughts on PDF and CDF and how that can be used in the simulation aspects of it, and then we will look at a simple illustrative example. Yeah, so this kind of demonstrate how the simulation, the aim is to how PDF, CDF concepts are implemented in simulation. Implemented in simulation. So, that is what we will be covering today in this present lecture. I gave it as lecture number 13, even though we are one of the concluding lectures. This is kind of the sequence of PowerPoint presentations that I have been doing, and you have seen couple of experts who have anyway come into the class and gave you different exposure to different other topics. So, without wasting much time, let us get into the basic definitions of it. The first thing that we talk about is random variates and simulation. Okay, and we are talking about random variates especially with respect to the simulation. So, in simulation we can always say this: in simulation the aim is to model some component or behavior of a system that is random or that is randomly behaving. Okay. So, major aim is to model some component or behavior of a system that is randomly behaving, or you can say that there has uncertainty with it. Uncertainty in behavior. Okay. We are not sure how it will work. Okay. We cannot really. So, this means predicting a future state is not completely accurate. You may predict that the future of the system might look something like this, but it could completely be something else. Okay. So, what we do is the aim is to model some component or behavior of a system that is randomly behaving, okay, that is random. Okay. So, the question then is, how do you do this? How do you do this? Okay. And the answer to this question is by using a distribution. What distribution? Probability distribution. Okay. A probability distribution that is right. Okay. So, for example, if the probability of values or values of the system is more near to the mean or expected value and less further away from mean, then normal distribution can be used. Okay. So, what it actually means is, in a normal distribution you have a mu mean here, and here is your standard deviation sigma, okay, the plus sigma minus sigma side, and the distribution will kind of have a shape something like this. This means that you have more probability. This is where, okay, higher probability close to mean. Okay. So, you have more probability that are closer to the mean, and this is low probability away from mean. Okay. So, such kind of a distribution can be used to model such a behavior of a system. Okay. See, if the probability of the values of the system is more towards the mean or the expected value, this is the mean. Okay. If the values are more towards this, then you can use a distribution like this where it is larger probabilities. So, the y axis of this has probability p of x is available here, or f of x, you can draw whichever way you want to draw it. Okay. And the probability is less if it is further away from the mean. So, this is the lesser probability that we are talking about both sides. Okay. So, if that is the case, then we can use a normal distribution to do this. But the problem is, what is the issue? Major issue is this, that usually we never know for certain what right is. So, one example is that some people can also model the same thing with using what we call as a triangular distribution. You can say here is a low value, here is a high value, and here is the most observed value. Then people can form a triangular distribution like this and say that this will also replace this. Now, this is called a triangular distribution. Now, whether the normal is better or triangular better, or which one is right, that is very hard. This is why what the right is a tough question for us to answer in this particular regard. Okay. So, how to tackle this? Okay. The way to tackle this is, we have some data or obtained some past data. Okay. So, somewhere we obtained some past data or we have some data and would like to match it, that data. So, somewhere somehow we obtained some data, some past historic data is available, and using that we would like to use the data, and from there it's plotted using different graphical systems and try to find out the patterns available with it. That is why we studied graphical tools in the previous stuff, and then we decide what type of patterns the data. So, from here what you are trying to do is, okay, this is where you are trying to do patterns in the data. Okay. So, you are trying to look for how the data actually behaves. Okay. Okay. So, ideally speaking, this allows to choose a theoretical distribution that best fits the raw data, best fits the raw data. So, let us say for example, you ended up plotting this using a graphical tool, and let us say you had various classes like this, and then you plotted it something like this. Let us say this is how you plotted it. Then you can say that to some extent you can kind of think about it as a normal distribution like this. Okay. So, that is kind of, you will say, okay, this is somehow fits the data. So, this is where the best fit theoretical, that is what we try to do in this regard. Okay. So, assume that you guys understand what I am trying to say in this particular case, but the aim here is that you are trying to study some component or behavior of a system that is random, okay, which means there is uncertainty in its behavior. You have there is a lot of uncertainty that is associated with this, and you are trying to find out, you are trying to because there is uncertainty, you are not completely sure what is going to happen in future. So, to model the system, what you do is by use a probability distribution is the thing that you think it is the right probability distribution. And like for example, I gave you the when people use a normal distribution, stuff like that. But the biggest issue in this regard is it is never know for certain what the right is. It is quite hard to figure this out. So, how do people tackle this problem? Usually you obtain some past historic data, would like to use a graphical system to plot it, and would like to find a patterns in the data that will actually match the data. So, just I showed you here, when you plot a histogram, and then you can see that maybe sometimes a normal distribution would fit better than a triangular distribution. Okay. So, what happens is once you look for the patterns, then you choose a theoretical distribution that best fits the raw data. So, the aim of the simulation is fit to historic data as a starting point. So, you have to start someplace, and the starting point in this regard is first start by fitting to the historic data, and then from there do the improvement. Okay. So, then the next question obviously is choosing the right distributions. Okay. Once you plot the graph and other things, there are quite a lot of empirical distributions from which we can do that. The first thing is that the modeler usually have some specific knowledge about the system, some specific knowledge about the system, that will suggest a particular distribution. Okay. So, what happens is you may have some very specific internal knowledge about the system, okay, some specific system knowledge which will kind of suggest you a particular distribution. Okay. If so, if you have that particular information, if so, then all you need is the parameter of the distribution, is the parameters of the distribution. For example, normal, then specify only mu, which is the mean, and sigma, which is a standard deviation. So, if you think that you are going to use a normal distribution, then all you need to do is specify the mean and the standard deviation. So, if you have some prior information about a particular distribution, then all you need is the parameters of that distribution. So, this is the advantage of using a distribution, is that once you can say this is the distribution. So, this distribution is this is the pattern. Okay. If you identify this is the pattern, then all you need to do is you specify the parameters of the patterns. For a normal distribution, it is the mu and the standard deviation. Okay. If it is an exponential distribution, okay, then only mu is needed, okay, or the mean is needed. Okay. So, like that. So, depending upon which distribution you pick up, you will specify only the parameters. So, this distribution means the pattern, depending upon the pattern, which actually comes from some specific system knowledge. Okay. So, some of the rules in this, okay, some considerations. Okay. Number 1, known characteristics of data can help. Okay. So, if you know some of the characteristics of the data, then it can help. Specific knowledge includes, okay, discrete or continuous. Okay. If you think it is a discrete system, then you might not be able to use a normal distribution. You might have to look at something else. Okay. Then some other part is range, which includes bounded, non-negative, finite, etc. So, for example, is your distribution going to infinity? For example, if you draw a normal distribution, this distribution actually we draw like this, but it actually goes to infinity. Okay. This is the minus infinity side, this is the plus infinity side. But if somebody says it does not go to infinity, it is a bounded distribution, means this is the stopping point and this is the stopping point, it does not go beyond that and this is the mean value, then you might want to think about a triangular distribution this way as well, if it is bounded. Okay. So, maybe if it is unbounded, you can think about a normal distribution, with a bounded one you can think about a the triangular distribution as well. So, these kind of characteristics, whether it is discrete or continuous, whether it is bounded, whether it is non-negative. If it is non-negative, then you might not be using a normal distribution, instead you might use a Weibull distribution. Okay. Whether it is finite, infinite, all those kind of things will help you to determine these kind of characteristics of data can help you determine which distribution to use. Okay. Number 2, non-characteristics of the system. Non-characteristics of the system. Okay. If you know some characteristics about the system, okay. So, some of the characteristics that can help is arrivals, okay, customers, entities. Okay. So, these kind of arrivals are often, or you can think about as mostly, arrivals are often exponential. Okay, which means this means time between arrivals. Okay. So, if you think about it, if this is a time axis going on like this is a particular point where customer 1 arrived, then there is another customer arrived, customer 2, then customer 3, then there is customer 4, then customer 5, like this happening. So, this is the TBA, time between arrivals. This is another time between arrivals, TBA 3 or something like this. Okay. So, these are all, these TBAs, they follow exponential distribution. Okay. So, this is what we are talking about here, is that arrivals are usually, most of the time, mostly, they are mostly exponential, right. B, next one, okay. Measuring errors are usually normal. Okay. That means you would use a normal distribution if you are quantifying somewhere like a quality gate where you are checking something and rejecting a product or something like that, then you would like to model this with a normal distribution. A normal distribution where the, so measuring errors means most of them will be close to the normal value or the mean value, and then they will change accordingly. Okay. Then the third one is time between failures of machines or anything or machines, okay, cannot be negative. Okay. So, you cannot, if the machine, if you think about it this way, if here is a failure, machine failure 1, then you cannot have a failure before this. The next failure can only occur, next failure can only occur in a positive direction. So, it could happen someplace here as a failure 2. So, this is the TBF, time between failures. Okay. So, this time between failures cannot be negative. So, that means you cannot use a normal distribution here. You might have to use a distribution that is positive in nature. So, here if you are modeling that, then your graph will probably be, this is 0 and this is positive infinity, and maybe you might have a distribution something like this, which you might say, okay, the probability of the next failure, or you might even say that I might use an exponential, does not matter, which some through some curve you will have, but the most important thing is this will be a positive value. Okay. So, the time between failures cannot be negative. So, these kind of internal informations that you have is very important for you to choosing the right distributions. Okay. Continuing in the choosing the right distributions process, there is some more thing. Okay. So, the third point that is usually very prominently used by a lot of the practitioners is, okay, follow a formal approach, that is, which is use a standard or commonly used, use a standard or commonly used goodness of fit test, goodness of fit test to match the empirical distributions, empirical distribution. Okay. The empirical distribution come from the data. Okay. To match the empirical distribution to the theoretical distribution. So, whatever the data that you are getting, the empirical distribution which is obtained from the data, and to match with the theoretical distribution, use a standard or commonly used goodness of fit test. The two most commonly used goodness of fit tests are chi-square goodness of fit test, chi-square goodness of fit test. Okay. The second commonly used one is Kolmogorov-Smirnov test, Kolmogorov-Smirnov, it is commonly known as KS. Okay. So, these are the two properly used or prominently used goodness of fit test. So, use either one of these tests and then try to match, you match using this test, you try to match the empirical distribution with that of the theoretical distribution. Okay. This is the formal approach, follow the formal approach. Okay. There are people who do this. Also, maybe follow a less formal approach. Okay. This is also another option of doing it. Pick a distribution, a theoretical distribution based on your hunch, gut feeling or experience, you name it whatever you want. Okay. Pick a theoretical distribution based on your hunch, gut feeling or experience, whatever it is, and then do sensitivity testing, sensitivity analysis or testing to see how much your choice influences the results. Okay. So, what you do is you pick a theoretical distribution, some theoretical distribution is picked based on your hunch, gut feeling or experience. People usually use the data to validate the gut feeling or experience, and then perform a sensitivity analysis to see what is the impact of the choice, how is the choice of that particular distribution influence the results. Okay. This is another approach that is also being followed. Okay. This is usually lengthy but commonly followed in industry. Okay. We sometimes nickname this as brute force approach to a large extent. Okay. Now, we have seen that the four kind of methods of choosing the right distributions. I will try to give you some practitioners rules in this regard. Okay. How do people who are practitioners or who are more involved in simulation actually do this? Okay. So, I will say it as simple rules of thumb. There is no what you call as scientific backing or anything to this, but these are from experience. Okay. People who work in the simulation area, these are some of the rules that we do. Okay. The first thing, if nothing about the system is known, system is known. If you do not know anything about the system, if nothing about the system is known, but have a bounded range, okay, this kind of a system, you do not know anything about the system, but you know that there is a bounding, okay, you cannot go beyond that. Okay. Usually from 0 to some value. If you talk about the production in a factory, okay, the minimum a factory can produce is 0. So, it is bounded in the minimum. The maximum we can produce is probably in an 8-hour shift 100, 200, 300, but you cannot never produce infinity. There is some limit to it. Okay. If that is the case, then we use uniform distribution as a starting point. So, we start with the uniform distribution. You do not know anything about it, but there is a bounded range. Then we start with the uniform distribution. Number 2, if little is known, if little is known and have bounded range, okay, then you can say first is plot relative frequencies and if a hump is noted or peak is noted, okay, then use triangular distribution. If it is bounded, okay, so let us say you have a minimum of 0 and maximum of some values and you plot it. So, if you do something like this, an example would be you take the relative frequencies. So, this is like x and your y is 0 to 1, okay, that is your relative frequencies, and you plot something like this, you get a observation something like this. Something like this. Then you can basically think about it as approximating it with the help of a triangular distribution. Okay. Number 3, okay, if variance is high or high variation, and bounded to left, which means positive values only, use exponential distribution. Okay. So, if you are thinking about a scenario where you plot the values and you get something like this, okay, let us say somewhere you get a frequency stuff like this, then you can think about it as a exponential distribution. This shows there is high variability in the system. Okay. High variability is also shown here, okay. And this is 0 and this is positive infinity this way, okay, or some particular value, okay. But this is anyway bounded to the left, which means it there is no values here, okay, bounded to left, okay. This is the case, then you use a exponential distribution, right. So I will give you some common distributions, okay. So common distributions and what do they mean, okay. So for example, the first one is Bernoulli distribution. Please read about these distributions, okay. Bernoulli distribution, and it is used for yes no responses, okay, or success fail cases. If you are doing a quality control stuff where you are doing rejecting and those kind of things, the rejecting bad products, then Bernoulli is a good idea. Then you have is binomial distribution, okay. It is used for sum of Bernoulli responses. Okay. So this means that if you inspect 20 bulbs, what is the probability that 2 bulbs are bad and that kind of questions, okay. So sum of Bernoulli, okay, Bernoulli summed up is binomial. Then you have is something called as negative binomial. Binomial, okay. It is used for measuring number of attempts to the kth event, okay. If you want something special, something to happen, some explicit kth event to happen, then how many attempts are required, how many attempts are required to reach the kth event or obtain the kth event is basically can be modeled using negative binomial distribution. Then you have something called as Poisson distribution, okay, and Poisson distribution is typically used for points in a given space, okay, and many people also call it as count number of arrivals, how many people arrived in a particular time period given the rate of what it is, okay. So we typically call it as point in a given space, that is a limit and within which how many points or how many arrivals, how many customers, all those kind of things are very well done with the help of Poisson distribution. Then we have is geometric distribution. I am talking only about the major distributions, nothing else, okay. Geometric distribution is basically measures number of trials until first success, okay. So if you are tossing a coin or rolling a die, and if you consider 3 as getting 4 or more as a success, then how many trials are required before you get a success? That can be modeled using a geometric distribution. So if you are getting raw material from a vendor, and if you are trying to find out how many parts need to be inspected before you get the first defective part, that can also be modeled very well using a geometric distribution. And the last one that is pertaining to us, I will write today as the multinomial distribution. Multinomial distribution, and what it does is it basically models the multiple possible outcomes of each trial. Outcomes of each trial. So what you are doing here is, let us say you are in a process of checking the painting of a car, and one painting can be good, another can be touch up, third can be repaint, fourth can be discard. So every car there is multiple options available to this, and which option will happen in the next one, it depends upon the way that can be very well modeled using a multinomial distribution, right. Now Continuing in the practitioner's rule, you should notice that in the previous case, all of these can be thought about it as these are discrete cases or discrete distributions. Okay. We are talking about counting individual. Okay. Each observation is countable. Now, when we talk about the for continuous cases, for continuous variables or random variables, when I say variables, I am talking about random variables. For continuous cases, if we the major distributions that we are talking about is normal distribution, okay. We can say it is the basis of most of statistical inferences, okay, heavily used for measuring errors, etc. So, normal distribution is used whenever you have a scenario where the probability of occurrence is an unbounded, there is no bound in this case, and probability of occurrence is around the mean value is very high, then that is where we use a normal distribution. Then we use, there is, let us say there is a distribution called a log normal distribution. And log normal distribution is commonly used to study environmental variables. Okay. If we are modeling and studying environmental factors or environmental factors, then we would end up using log normal distribution. Okay. Gamma distribution. Okay. That are commonly used to study time to failure. Okay. It is also models radioactivity. We studied about the gamma decay, gamma function that suggests about how the radioactivity actually works, but mostly time to failure is very well modeled as gamma distribution. Then there is something called chi-square distribution. Not chi-square, chi-square distribution. Okay. Chi-square distribution is usually the it is a family of distributions, but you can say that how variation or variance behaves. Okay. When we are trying to model variances, then you can use chi-square distribution. You can also talk about F distribution. This is also another specific case of chi-square distribution, and this also is used to model variance. Okay. Then you have T distribution. This is a student, some people call it also as the student's distribution for statistical tests when sample size is low. Okay. So, that is the T distribution aspect. When you have low sample size, that is when you use this. Then you have something called as viable distribution. Okay, viable. Viable is to use to study lifetime of a system or a product. Okay. If you are trying to study life cycle of a system or a product, then you use viable distribution. Then you can also talk about as extreme value distribution. It is another one that is used. Okay, both type 1 and type 2. Okay. These are also used for lifetime of a system or a product studies. Okay. So, these are all for the continuous random variables that I talked about. Okay. So, just to say continuous random variables are defined for continuous numbers on the real line. Okay. So, in the number line, when we have the real number line, that is where it is. Okay. So, here you say that implies the probabilities have to be computed for all possible sets of numbers. So, here you are more looked at a set of numbers or an interval of numbers. Okay. Interval of numbers. Okay. So, you are trying to, so for example, if you are doing a uniform exponential distribution or gamma distribution which looks like this, if somebody asks what is the probability of this particular case, probability of x equal to x, that does not make any sense. Okay. You can call it as x1 and you can have another probability of x equal to x2. Between this, what is the probability between this can be calculated by integrating minus x1 to x2, okay, e to the power of minus x or whatever the function that you want to call it, okay, and then you can get the value accordingly. All right. So, the continuous probability distributions for the continuous cases, these are the specific things that you actually work on. Okay. Now, if I tabulate all of these things into a particular format, okay, choosing the right distribution as a so this tabulation is for a quick reference. Okay. This is based on experience. Okay. This is a not hard and fast rule. Okay. So, consider these as rule. Consider these as guidelines. Okay. These are guidelines for you to decide which distribution to use. Okay. So, this is the characteristic, which means characteristic of the system. What are the characteristics that you are noting? Okay. So, the first thing that you do is high variance, okay, or some people also call it as high variability. There is high variance in the system, okay, and bounded to left, which means values is greater than equal to 0. There is high variability in the system, the values are greater than or 0, unbounded to right, which means all way up to positive infinity. So, if there is high variance or high variability in the system, okay, or the points are highly varying from the mean value, it is bounded to left, which means that all the values are greater than 0. This means positive values only, okay, only positive values, and it is unbounded to right, which means a very extremely, so unbounded to right also means extremely large values are possible. Okay. So, that is what unbounded to right means, very large value, extremely large values are possible. If that is the case, which distribution will you use? The distribution to use is exponential. Okay. You would end up using an exponential distribution if the extreme large values are possible in this regard. Okay. So, as the first rule of thumb, high variability, high variance, bounded to left or positive values and unbounded to right or very large values are possible, then you end up using an exponential distribution. Okay. Then either it is symmetric or non-symmetric. Okay. So, which means, okay, symmetric about a specific value, okay, and bounded on both sides. Okay. So, it is very large values not possible. Then if this is the case, if it is symmetric or non-symmetric, bounded on both sides, then use a triangular distribution. So, the exponential distribution, if you draw, it will look like this. Okay. P of x, the distribution will look like this. Okay. It will continue like this. So, this is 0. So, it is bounded, no negative values are allowed and only positive values, and it goes all the way to infinity, right. A triangular distribution you can draw if it is like this. Let us say you have a minimum value, maximum value and a common value, then you can draw a triangular distribution like this, which means it can be symmetric, or you could have a triangular distribution which is A and you have a B and you have a, let us say, C. So, then you can have a triangular distribution of this fashion, which is non-symmetric. This is symmetric, this is non-symmetric, that kind of a, but these are the, this is bounded, both the cases are bounded within the limits. All right. Now, the third one, okay, all values are equally likely, that means and bounded on both sides. Okay. So, there is very large values not possible. Okay. Every value has the same probability. Okay. If that is the case, all values have the same probability and very large values are not possible. If that is the case, then you use uniform distribution. Okay. Typically, a uniform distribution is drawn something like this. You have a value A and you have a value B and you have a probability of x, and all values between this will have the same probability. Any value between this, any value is equally likely, and these are bounded. Equally likely means they all have the same probability of occurrence. So, then the uniform distribution allows you to model a system which are bounded on both sides, extremely large values are not possible and all values within that are equally likely. Okay. Then the last more common case that we use is if it is symmetric. Symmetric means, you know, equal about a specific point, okay, or symmetric, or you can think about as mirror image. Okay. And it is unbounded on both sides, extremely large values possible, large values are possible, okay, and can be negative. So, not bounded on left. If this is the case, you use a normal distribution. Okay. And the normal distribution is something like this. You have a mu and you have your standard deviation and you draw it as a symmetric distribution about the mean. Okay. So, this is the symmetric, okay, and you have variance on both sides, okay, 1 sigma, 2 sigma, 3 sigma like this, minus 1 sigma, minus 2 sigma, minus 3 sigma like this. Okay. So, that kind of a distribution is where we use as a normal distribution. Okay. So, these are like, so at least ensure that these 4 distributions are studied properly. Okay. About 80 to 90% of cases can be modeled by these distributions. Okay. So, what I am saying is that if you know these 4 distributions, if you study them properly, understand them from a good standpoint, then about 80 to 90% of the cases can be modeled using this distribution. Okay. So, with this what we will do is we will take a quick break from this today's lecture, and what we will do is we will continue the remaining of the lecture after a short break. Thank you.